or you know your T, right? So this is the part that you don't know, right? So it's thin wall analysis, right? Your Vx is going here. You're going to sketch your shear flow. Okay, so your shear flow, your structure will look like this. Thin. Then at the center is the longest, right? So you realize that this is a what? You guys will say, oh, here we go again. So this is going to be our, this is our what? This is going to be our white flange, right? So the analysis, so thin wall, hey, yeah, I'm going to write in pink. Thin wall, white flange, analysis, right? So when it's thin wall, white flange analysis, there's only one Q, right? Because they have two separate start. So this is your start, number 1, start, number 2, and the end point is also separate. End point number 1 and end point number 2, right? So the only first moment of area that you need to find now, right? The only first moment of area that you find out is from here to here, where I'm highlighting. You can see the highlight, right? So where this stop. That's it. Okay, that is the first moment of area. So you're like, can you all remember? Yes or no? Or you guys like okay, right? You now this is multidisciplinary. Okay, that's where this is really useful stuff for all of us. Okay, when we have detailed analysis now. Okay, it's not just force divided by area, my over I. Now we have to combine all of them now. Okay. So we have to find the first moment of area over there. Okay. So like what I said, so I'm also a bit confused now. Okay. So we have to find QY. So it's equal to area. Okay. Area. So QY is area multiplied by X distance. Right. So why is that? So QY means first moment of area about the what? Y-axis. So we're going to take first moment of area on this axis now. Okay, on this axis that I'm going to highlight now, right? On this axis, we're going to take first moment of area on this axis now, right? Right. That's the axis that's fixed, right? And then the highlighted one is the what? Is the area. So the perpendicular distance now, right, is this distance, right? So this is the centroid of this particular area, right? And this is the distance. So that distance is what? Is our X distance. It's not the what? It's not the Y distance. So a lot of times we get confused. Okay, a lot of times, what is this distance? Yes or no? Okay. So now once we know this distance, okay, so we are aware that the distance from here to here, right, is 75 millimeters. This is given. And the distance from here to here, right, so that's our BF is 166. So 166 divided by 2. Okay, so this is, sorry, what am I doing? Messing around. You guys should not do apologize. So this is 166, right? So this is 166 divided by 2. So what we are trying to achieve down here is we want to calculate what is this distance. We want to calculate what is our X distance. Okay. So the area, right? So now you guys are aware that Y is first moment of area about Y axis is A x bar or ax. Okay, so we calculate qy. So I'm going to use more down here. So qy. So the thickness is going to be what 11.8. Is it 11.8? Yep, 11.8 times 10 to the power minus 3. The depth is 75, so the area is 75. Why 75? Because of the 4 rules. Yes, no. The analysis is the analysis starts from x max. Okay, so x max you draw back. So this is 75 times 10 to the power minus 3. So this constitute the area, and then y bar, sorry, x. Okay, now x is equal to, so 75 or 166, 0.166 divided by 2, right? So this is, sorry, 0.166 divided by 2, right? And then minus by 0.075 divided by 2. Okay, so this over here is your x, right? So this will come out to be 11.8 or 0.166 divided by 2 minus by 0.075 divided by 2 times by 75 power minus 3 times by 11.8 power minus 3. So it's equal to 40.2675 times 10 to the power minus 6 meter cube. And then finally, now you have everything now. Okay, now you have everything now. So now you calculate your shear in your xz direction is equal to your shear, your zx direction. So this will be equal to V. So the V is 16 times 10 to the power 3 divided by I. So V and I are always constants regardless of the position that you're interested. Still the same rules. Q changes. Now I, right? I will be equal to what? I will be equal to sorry, T will be equal. Sorry, T will be equal to what's our thickness? 10 point. I think it's 10 point. So sorry, it's 11.8 times 10 to the power minus 3. Okay, so this will be equal to 16 power 3 times by 40.2675 power minus 6 divided by 9.03 power minus 6 divided by 11.8 power minus 3. So it's equal to 60465. Right, 60465 times 10 to the power 6 Pascal. Okay, and the direction based on the shear flow is going towards the left hand side. You have to know the direction. Okay, now I'm going to not hurt your brains, but I'm going to ask you guys a question. Before I ask my question, any of you have a question, please? Anyone, please?
Yeah, I got a question.
Yep.
Why did you start the analysis for the first moment of area from the left side and not where it starts from the start?
Because I like your question. So you asked me why I start from here, right? Right? Why this is the sorry. You mean the why I call this a start? Is that what you mean, or why I started from the end?
Well, either.
I like that. Okay. When I wrote the start and the end is to show you that that the Q is only one Q. You don't need to do two Q because it's white flange. Number one. Number two, when you ask me why I started from the outside in, because of our rules. Our rule says what? Our 4 rules. That the datum is at the centroid, and then the analysis starts from where? X max. Yes or no? Hello?
Yeah.
Yeah, that is why. Yes?
Yeah.
And then the first moment of area cannot cross the what? Cannot cross the centroid. Yes or no?
Yeah.
Yeah, that's why. I think you just forget. Okay, so in terms of analysis direction, right? This is the analysis direction for the shear. Okay? Right? You remember now, right? Yes or no?
Yep.
How you're right, you remember. That's why this topic is not difficult. The difficulty is when you have to integrate everything together, and we're not done yet. And we're not done yet. Okay? Okay, we're not done yet. Okay. So we have done one force already. So the next one, okay. Now I'm not saying it get worse. Okay, now it's like here we go again. Okay, so we have done. So I'm going to half my page. Okay, so we have done. Right, so we have finished dealing with Vx. Okay, so we have finished dealing with Vx now. Right, so now we look at Vy. Okay, now we look at Vy, and we look at Vy, right? So I think I made a mistake down here. Okay, my apologies. Vy is not equal to 0. Okay, and I made a mistake. My bad. I made a mistake. Okay, Vy is not equal to 0 when it's thin wall. My bad. Okay, when it's thin wall analysis. Okay, my bad. Okay, so this is thin wall. If it's thick wall analysis, is equal to 0. This is a thin wall analysis. Okay, right. So now I'm going to do Vy now. Okay, I hope I can copy this image first. Don't allow me to copy. Yep, you know. Okay, so I'm gonna go here. So this is our. So we are going to find Okay, we're going to find the shearing stress induced by Vy. Okay, so if we look at Vy from this view, Vy is coming in this direction. Okay, Vy. So this is our Vy. Is coming at 25 times 10 to the power 3 Newton. Right? Vy is coming out at 25 times 10 to the power 3 Newton. What is the stress that we're going to generate for Vy? It's a shearing stress. But it's interesting, right? The shearing stress is it the same direction, or is it in the same plane as Vx? So where is Vx, right? Vx is here, right? I don't know about you guys, but I'm getting so excited. There is our Vx, right? Right? So our Vx is generating a shearing stress in a xz, which is equal to a shearing stress of our zx. How about Vy? Anyone? Anyone? Is it going to generate shearing stress in the same orientation, or in the same plane? Means, is it going to be also in the xz and yz? Oh, sorry, xz and also equal to zx. Anyone?
Wouldn't it be YZ?
I love it. Yeah. So right. I love it. Okay. So I'm gonna. So you say, isn't it YZ, right? I also thought so initially. I also thought so. Okay. So I'm going to draw this. Okay, I'm going to draw this. Right. So we have done this. Right. So we draw this. Right. So this is due to Vx.